This is problem 342. We're considering a tube wall of inner and outer radii, Ri and Ro. Let's draw a diagram here of a tube. Inside radius of Ri and outside radius of Ro. Give the tube a length L, whose temperatures are maintained at Ti and To respectively. So the inside wall is at Ti and the outside wall is at To. The thermal conductivity of the cylinder is temperature dependent and may be represented by an expression of the form K is equal to K sub O times 1 plus AT, where Ko and A are constants. So that and that are constant. Obtain an expression for the heat transfer per length of the tube. So what we're going to find with this, part A, is we want to find the heat transferred per unit of length of the tube. So this will be QR prime, which is defined as Q in the radial direction divided by L. Then the second thing it's going to ask is, what is the thermal resistance of the tube wall? So we're going to calculate RT prime, which is defined as R sub T times L. So those are the two things we're going to get here out of this problem. Now this problem is a little bit tricky because at first glance we look at that and think that it doesn't fall into the mode of a typical alternate conduction analysis problem, but believe it or not, this actually is the case, as I'll show you here. The first thing you need to know is that we have to put an assumption here. The assumption is that everything is at steady state. Just because of the way the problem is worded, there's no reason to believe there will be any sort of transient effect. So we'll assume everything's at steady state. And if everything is at steady state, with the inner and outer temperatures of the tube wall being fixed, then it can be assumed, because this is a chapter 3 problem, it's one-dimensional conduction, we would get then QR is equal to a constant. So what we're going to do then is we're going to go ahead and define then what this radial heat transfer is. So QR, as we know, is going to be minus K times A, which is a function of R, times the change in temperature with respect to R. But as we know here, K is a function of T, but T is also a function of R, and A is a function of R, so it gets things a little bit tricky. So let's remove this and let's make it a little more accurate here by saying K is a function of temperature and then area is a function of R. So we can go ahead and put in what those values are. The value of K, we know, is going to be Ko times 1 plus A times T. And then the area as a function of radius is 2 pi R times L. And then we have dt dr. Now the next thing we can do then is we notice that we have the L on the right-hand side of the equation and the QR on the left side, and you notice that we're trying to find QR prime, which is defined as QR divided by L. So we'll go ahead and do that division here and say QR prime is equal to QR over L, which then gets us KO 1 plus A times T times 2 pi R dt dr. So if you look at this equation now, notice that it's not something that can be solved easily mathematically on the right side, because you have this extra value of T for temperature, and then you have also an R. So we have now our two parameters on the right side, which prevents it from being easily solved. But one thing we can do is, with our assumption of above a steady state, is we can say this whole thing is a constant. And since QR prime is a constant, we can do a separation of variables, which is the typical approach you would use to solve an alternate conduction analysis. So let's move all the R's to the left side, and in doing so then we get QR prime times dr over R. Then on the left side we get minus 2 pi Ko 1 plus AT times dt. And just like with the alternate conduction analysis that we know, we're going to integrate this between the two radii, Ri and Ro, and the temperature associated with Ri is Ti, and the temperature associated with Ro is To. So now we can do some integration, and this will enable us to get the value of heat flow per unit length. So the left side then, if we do the integration, dr over R, we integrate that out, get log of R. Since QR prime is a constant, we get QR prime times the natural log of RO minus natural log of RI. And we can use our trick with natural logs and combine them, such as they're now RO over RI. On the right side, we can take the 2 pi KO and the negative sign out. So we're going to get minus 2 pi KO. And notice that this is two terms then. We have one term that's just dt, and we have another term that's AT dt. So when we do the integration of that, for the term that's just dt, we're just going to get simply TO minus TI. And then the second term, we're going to get then A over 2 TO squared minus TI squared. What we'll do now is we'll move the log of R over Ri over to the right side so we can finish off this problem here. QR prime is minus 2 pi KO times TO minus TI plus A over 2 TO squared minus TI squared, all divided by natural log of RO over Ri. So this is the answer, and this allows you to solve for the heat flow per unit length. However, we can do something a little bit better than this. Let's explore the influence of the temperature dependence on our answer. So what we'll do is let's take the negative sign and incorporate it into the brackets here. And we're also going to take out of the second term here, the TO squared minus TI squared, we're going to take out of it a TO minus TI. We know that when we have a difference of squares, this is the same thing as TO minus TI times TO plus TI. So when we do that, this simplifies then as 2 pi KO over natural log of RO over Ri times TI minus TO. And then we're going to have this other term here, which is going to be 1 plus Q over 2 TO plus TI. So what makes this a better looking result, or more interesting result, is this left side here is what you would get if K is constant. The right side is what you get from the temperature dependent K. So that extra temperature dependence, the fact that K is equal to KO times 1 plus A times T, that AT term results in this extra temperature dependence over on the right side. So that's how that influences then the answer. So if we want to box it out, we get QR prime is equal to that right there. I'll go ahead and bring down QR prime. So that's the answer to part 1. For part 2, it's a really quick result here. So part B, we're going to find the thermal resistance RT prime. And in doing so, we're used to using just RT without the prime. So R sub T is going to be your delta T over Q sub R. Now, when you go back to the picture here, we should have shown this to you in the beginning. Q sub R is going outward radially, like so. So we are drawing QR as going radially outward, so therefore, in order for Q sub R to be positive in the direction shown, we must have TI be bigger than TO. So our delta T then is going to be TI minus TO over Q sub R. Now R sub T we defined as RT times L. So what we can do then is say that R sub T is RT prime divided by L. And we can do then is we can rearrange this now as RT prime is going to be TI minus TO Q sub R divided by L, which gives us TI minus TO over QR prime. So all we need to do then is take our answer for part A and then stick it into the denominator for part B, and then we're done. So what we get then is RT prime is going to be TI minus TO divided by our answer for part A, which we can extend this out here, will be 2 pi KO natural log of RO over RI times Ti minus To with 1 plus A over 2 To plus Ti. So, of course, what happens now is the Ti minus To's cancel out, and then we're home free, so that cancels out with that. And what we get is natural log of Ro divided by Ri, or 2 pi Ko. So I'll put that in brackets, and I'll say 1 plus A over 2 To plus Ti, the whole thing to the minus 1. So again, the interesting part of this is that the thermal resistance here for this is what you'd get if you just had a constant K. And then the temperature dependence is incorporated as some multiplying factor onto the original term. So let's box that out, and we're done.